As you can see, glacial melting, past, present, and future. How much, how fast, what impacts. A tribute to Ben Flower, as I went through yesterday. Ben had a lot of his research interest in the polar system. And we're going to continue in the, with meltwater and associated linkage to the polar system. Today we're going to go into the polar system, both in the mono system, but this time we're going to move towards the Antarctic, as well as we're going to, for those that are biologically inclined, move more into the biological system, which is a nice change. I'd just like to introduce Amelia Chavanel, who will introduce our speaker.
And then Mike will introduce somebody else and me. So it's my pleasure to welcome Mike Meredith from the British Antarctic Survey. And for all of you students out there, this is a great little lesson. So Mike became one of my Facebook friends, but we hadn't actually met until, when did you arrive?
I'm not sure.
A couple days ago, Tuesday. And so I had known about his research for a long time, but we had not met in person. So who is Mike and what does he do? Unclear, but he did get his PhD from the University of East Anglia, and the title of his dissertation was on the temporal variability of transport through the Drake Passage, which he still investigates periodically on various Antarctic research vessels. And so Mike has spent 59 weeks at sea. And when he's not at sea, he is the leader of the Polar Oceans Research Program at the British Antarctic Survey. He's also chair of the Southern Ocean Observing System. And he has an appointment as well with the Scottish Association for Marine Science in Oban in the UK, which is sort of a translation for where we go to fly fish. And so Mike will be presenting topic today, rapid change at the Antarctic Peninsula, causes and consequences. And in case you were wondering by his accent, yes, he actually has met the Queen. You can ask him about that in questions. So it's my pleasure to introduce Mike Meredith.
Okay, thank you. I'm not quite sure what to say following that, but if the science is boring, we can talk about the Queen instead, if you prefer. That would be fine. Just building up the tension here. This is what we're doing. Here we go. Thanks very much. Thanks. So, yeah, it's a very great pleasure to be here, and I would like to thank very much the people that have organized this seminar series for inviting me and giving me the chance to come along and tell you some things about the Antarctic and why I think it matters and why I think it's an important subject for research. I'll say at the start that I'm unusual in the context of this room, not just because of my accent, but because I never actually got to meet Ben Flower. I knew the name and I knew the science and I heard very good things, but unfortunately he passed away before I had a chance to meet him in person, and that's something that I regret very much. All I can say is that I hope that Ben would approve of the talk that I'm now going to give in his honor. It doesn't really matter whether he would have agreed with everything I'm going to say or not, because that's not the point. But I think, well, hopefully he would have enjoyed it anyway. So the title of the seminar series, Glacial Melting, Past, Present, and Future, How Much, How Fast, What Impacts. The bits I'm going to really talk about are mainly present, because I'm an oceanographer. I'm an observational oceanographer. I deal with actual measurements of the ocean. And in relation to how much, how fast, and what impacts. Well, after Ian's talk yesterday, how much, the answer seems to be we don't know. How fast, the answer seems to be we don't know. And what impacts, that's the bit I've got to try and answer. So already you can tell what the answer to that's going to be, but we have some ideas at least. And I'm going to talk specifically about the Antarctic Peninsula. It's a great place to look for impacts of glacial melting because it is somewhere that's warming very rapidly. So it's one place that we know glacial melting is happening. And it's one place we can get to relatively easily in Antarctic terms in order to study it. And in case you're wondering, this is a picture of the Antarctic Peninsula. I took this picture there 2 or 3 months ago myself. It's the most stunningly beautiful place I think I've ever been to. I know some of you have been to it. If you haven't, then you really should before it all melts, before it goes. But that's what it looks like kind of now. So why do we care about the Antarctic Peninsula? This is kind of what I alluded to. It's changing very rapidly. It's a hotspot of global climate change. Climate change, the planet is warming, but that warming is not evenly distributed across the whole planet. This shows surface atmospheric temperature trends during the second half of the 20th century. And you can see that there are 3 big hotspots of regional warming. 2 in the northern hemisphere on the fringes of the Arctic, and 1 of this region here. This is South America here, in case you can't see that. This is the Antarctic Peninsula and the bits of ocean adjacent to it. It's warming more rapidly than anywhere else in the southern hemisphere. So if you're interested in the oceans, if you're interested in marine biology and you want to understand how that's going to change as the oceans warm, this is a fantastic place to go and study because it's happening here now. In essence, it's a superb natural laboratory to study the effects of climate change. This re-emphasizes this point to a large extent. Climate change around the Antarctic is very regional. Warming is strongly concentrated over this area at present. Around the rest of Antarctica, the climate change is much more diffuse, lower levels. There's cooling in places. However, everything that we know, or that we think we know, based on models, suggests that this is going to change over the course of this century. As greenhouse gas warming progresses, what we're going to see, we think, if we can believe the models, is that this warming is going to progress much more evenly and circumpolarly around the rest of the Antarctic. This is a projection from Tom Bracegirdle based on a range of IPCC class models with a clever averaging technique that he uses. And you can see everything that's red and yellow is warming. So Antarctica itself, over the course of this century, is predicted to warm. The surface of the Southern Ocean is predicted to warm. Sea ice is predicted to retreat everywhere. So what we can do is look now at what's happening at the peninsula, and we get advanced insight into feedbacks and processes and things that are happening there that might happen around the rest of Antarctica during the course of the next century. So the Antarctic Peninsula, hopefully you're convinced it's a place that is worth studying, is worth investigating. It's changing rapidly. We know a lot about what's going on at the western side of the Antarctic Peninsula, less about what's going on at the eastern side. And the reason for that is that within the Weddell Sea here, there's an awful lot of sea ice. It's there a great deal of the time. Often it's very hard to get down to these regions here on the eastern side of the peninsula to actually make measurements. It's not impossible, people do it, but it's difficult. The western side, the climate is generally much warmer. The data sets we have from the ocean are much more rich and much more diverse, so we know a lot more about what's going on. And one thing we do know is that these 2 different sides of the peninsula, they matter in different contexts. They behave in different ways. The implications of the change on the 2 different sides of the peninsula are actually quite different. What this plot shows, in case you're wondering, this is surface temperature change in the ocean during the second half of the 20th century. There's big areas where there's no data, these white areas, and these pinks, the warm colors here, show a very strong rate of warming of the surface ocean. These are some very big numbers, even by Southern Ocean standards, and the Southern Ocean is itself warming faster than the global ocean as a whole. And there are implications of that for the sea ice, there are implications for the marine ecosystem on the western side of the peninsula. So on the eastern side of the peninsula, things are a little bit different. On the western side, it's very warm. You're very close to the circumpolar current, and warm water comes up onto the shelf. The eastern side is a lot colder, and the reason we care about the eastern side of the peninsula, well, there's a number of reasons, but one of the ones that matters the most to me is the site of formation of Antarctic bottom water. And Antarctic bottom water is the coldest water in the global ocean circulation. It's the densest water. So what happens is it forms in a range of places around the Antarctic continent, and it sinks to the seabed, and then it spreads northwards along the bottom of the global abyssal ocean. And what this plot here shows is the fraction of abyssal waters in the globe that was sourced from Antarctica. So all these blue colors, this shows water that's formed around the fringe of Antarctica and has spread northwards. And you see it's only really the North Atlantic where there aren't very substantial contributions of bottom water from the Antarctic. So it's a globally important water mass. And what we do find is some sources of this water mass along the eastern side of the peninsula. So the Antarctic Peninsula is here. This is the Weddell Sea. These dark blues are some of the sources of Antarctic bottom water. I hope you can see this. There's a light blue there as well, which is another source. This shelf region here, immediately to the east of the Antarctic Peninsula, is where you get some very dense waters formed, especially in the wintertime. And these spill off the shelf and then they flood northwards. And this sword in particular flows northwards up the Atlantic. And what I'm going to do is I'm going to persuade you that fresh water is one of the key parts of this system. And if we're going to understand the system at all and the implications for climate and the implications for ecosystem, what we really need to do is understand the freshwater system as a priority. The freshwater system of the Antarctic Peninsula is changing, but it's composed of many different things. And each of them are changing differently. And so what we really need to do is try and understand them separately if we're going to gain any predictive skill about how combined they're going to influence the system into the future. So these are just some indications of how different parts of the peninsula freshwater system are changing. This is a plot from Alison Cook, who also works at BASS, about the glaciers along the Antarctic Peninsula and whether they're retreating or advancing. All the blue dots show the glaciers that are in retreat. All the red dots show the ones that are in advance on the western side of the peninsula. And you can see there's far, far more blue dots than there are red dots. There's far more glaciers that are retreating than advancing. And the retreat rates are actually accelerating. So that's more glacial ice leaving the land-based systems and entering the ocean. As well as that, the sea ice system is changing. And this matters in a number of contexts, some of which I will come on to. But what you can see here, this is the duration of the ice season circumpolarly around the Antarctic. And what you see here, adjacent to the Antarctic Peninsula, the ice season is shortening, and it's shortening very rapidly. With other plots, you can see that the sea ice extent is retreating, ice concentrations are dropping, and that's consistent with the very rapid rates of warming that we're seeing here. But you can also see that it's not the case that this is happening around the rest of Antarctica, and indeed, you see in the Ross Sea sector here, the sea ice is actually increasing very rapidly. And if you take a circumpolar average of sea ice around the Antarctic, it's actually going up slightly at the moment. Not by very much, but by a significant amount. But what you can see is that slight increase is actually the difference of two large numbers. It's really a very large increase here minus a very large decrease here, and the decrease is just slightly smaller than the increase. I'll come back to that later on. And another thing about the western side of the peninsula that we know is that precipitation has increased over the last century. There aren't very many good records, direct records of precipitation, but people take shallow ice cores, and you can see the layers year by year. They're built up each precipitation season. And by looking at the thickness of the layers and understanding how that ice works, they can reconstruct precipitation. And in places, it's doubled on the western side of the peninsula, and that's related to changes in atmospheric circulation. So each of these components of the freshwater system is changing. And if we want to understand how they're changing and how they interrelate and how they impact on the ocean and biology, we've really got to understand each of them. This will be the one that I'm really going to concentrate on today, though we can't ignore these because they do influence the other ones as well. So that was mainly about the western side of the peninsula. This is one of the contexts about how freshwater has changed on the eastern side. And this is one of the plots that Ian refused to show the movie of yesterday. I'm not going to show a movie either. But essentially, this is the collapse of the Larsen B Ice Shelf in 2002, which is towards the northern end of the eastern side of the peninsula. And you can see how dramatic it was. I mean, it's now you see it, now you don't. In the space of a few weeks, the ice shelf had collapsed and moved away. And Ian explained in very nice terms some of the processes behind that, so I don't need to go into that in detail. But a key thing to remember is that it wasn't just the loss of this ice shelf that happened. All the glaciers that were being buttressed by this ice shelf, they surged. Since then, they've slowed down, but they still are discharging fresh water into the ocean at a rate that's faster than they were when Larsen B was in place. So that's an introduction to the peninsula. Why do we care, really, about how this fresh water is changing and glacial melt inputs to the ocean? What are the reasons that we want to understand it and hopefully get some predictive skill as to how it's going to change in future? And there's a number of reasons. In fact, there's dozens and dozens of reasons. But this is just to draw out some of the ones that are most relevant to this talk, or possibly the most persuasive. One is that ocean salinity dominates ocean density at low temperatures. So when you've got very cold water, the temperature of the water can change, and it doesn't change the density very much at all, whereas salinity does. So relatively small changes in the freshwater inputs can have relatively large changes on the stratification of the ocean, dense water production in the ocean, geostrophic flow in the ocean, and so on. These changes in glacial ice can also have impacts on primary production in the ocean. There's a number of different ways that they can do that, not just by influencing things like the stratification of the ocean, but they can be a source of micronutrients. The Southern Ocean, you probably know, has large amounts of the macronutrients. So there's large amounts of nitrate, silicate, phosphate around pretty much the entire Southern Ocean, including the circumpolar current. But typically, productivity levels are quite low. And the reason for that is that the micronutrients, like iron, are in relatively short supply. And that's why if you go downstream of some of the islands in the Southern Ocean, like South Georgia, you can see these big phytoplankton blooms just in the trail as the flow picks up iron from the island sediments or from runoff from the islands and advects it downstream, and you get these huge phytoplankton blooms in their wake. Around Antarctica itself, there's also strong productivity on the shelf regions around many places. And it's believed that one of the sources for the iron to promote that blooming is glacial ice discharge. So the glaciers can flow over the sediments and the rocks underneath, and they can scour up the iron from those and discharge it to the ocean. And that supports the phytoplankton production. And there's a numerous other regions as well to do with organic pollutants and sea level rise, all of which are very important, but I'm not going to go into too much detail about today. So there's two parts to today's talk, essentially. The first part is I'm going to look at freshwater changes on the western side of the Antarctic Peninsula. And then the second part, I'm going to look at the impacts of changes in the freshwater system on the eastern side of the Antarctic Peninsula. And for the western side, I thought what I'd do is just give you a little background as how we actually determine what the different freshwater inputs are to the ocean. The issue we have is it's very easy to go and measure the salinity of the seawater and then come back a week later or a month later or a year later and measure it again and say, has the salinity gone down? If it has, then fresh water has been added from somewhere. But that doesn't tell you anything about where that fresh water came from. And if you want to understand the source of that fresh water, you need extra information. You need to measure another tracer in addition to the salinity. And so what we do is we measure oxygen isotopes in seawater as well as salinity. So this is just a little background. Most of you know this already, so this will be revision for you. But in case you don't know, all fresh water is H2O. All water is H2O. But all H2O is not the same. Most water, the oxygen atom has got an atomic weight of 16, but there's a small but measurable part that's got an atomic weight of 18. And so what we do is we measure the relative abundances of these different molecules relative to a standard, and we create a number called delta O18. And that's incredibly useful in this context of identifying different freshwater sources. The reason it's useful is it's a conservative tracer like salinity. Once it's in the ocean, it's only changed by mixing. It's determined at the sea surface by the different freshwater inputs. But you get an extra degree of freedom. Essentially what happens, this is This is real data of delta O18 in salinity. There's actually quite a lot more around the Antarctic than is shown here. This is model output, but you can see that in the sort of equatorial regions and tropical regions, the delta O18 values, these are quite high. You probably can't see those numbers. That's around about 0 or so. But as you move towards Antarctica, you move towards the South Pole, these numbers get lighter and lighter and lighter. So although salinity and precipitation is 0 everywhere, the O18s have different values. And this is for Antarctica itself. This is the O18 values of the surface ice over Antarctica. They're shown as positive here, but these are actually negative numbers. And you can see over the sort of plateau itself, you're getting some incredibly low numbers, minus 50, minus 60 per mil, and around the fringes, minus 10, minus 20. These are very low numbers. The way we use these, and the way we use that fact, is to actually decouple the freshwater budget. Because what we're going to get, we want to use that fact that precipitation is very isotopically light near the poles to separate it from sea ice melt. And I'll try and explain that here. Meteoric water, which is fresh water that relates to meteorology, so it's precipitation, or glacial ice, which fell as precipitation and is then discharged to the ocean, as I said, is very isotopically light. Sea ice melt has values that are very much higher. So although these two different sources of fresh water have got salinities that are nearly identical, the difference in O18 gives you that extra degree of freedom that you can use quantitatively to determine the different sources. And you can understand that here if you look at this cartoon plot. Essentially you have salinity here going from 0, which is pure fresh water, up to 35, which is pure ambient seawater. And if all you had was sea ice forming and melting, essentially all your data points, when you plotted O18 on this axis, salinity on this axis, would lie along this line. Now, conversely, if you had a system where you had seawater here and just meteoric water here, so precipitation or glacial melt, all your data points would lie along this line. And in reality, you have both, so you have these data points in between. And we use that to decouple the freshwater budget. So where's the data from? That's what we've been measuring, and this is where we've been measuring it. This is the Antarctic Peninsula. This is a schematic of the ocean circulation there. Don't worry too much about the details. This is just to show where we've been measuring. This is Adelaide Island here on the Antarctic Peninsula. And we have one of our research stations here, so we have easy access to the ocean. This is a research station that's manned year-round. There's always people there, and there's always the ability to go and collect samples. This is zoomed in on Adelaide Island on the western side of the peninsula. Rotherham Research Station is out here. And this is one of the local manifestations of climate change. This is the big glacier that empties from the southeastern side of Adelaide Island. This is the Sheldon Glacier. You might be able to read these numbers. This glacier was more or less static for many, many decades, and then in recent years it's just been retreating very rapidly. And obviously all this glacial ice that was here has been discharged into the ocean. And we're wanting to understand what that's doing to the system. So what we have is a program based at Rotherham where our brave marine heroes go and collect data for us pretty much every week within this region of the Antarctic Peninsula. And in summer, it's relatively easy because you can use inflatable boats and you just go out there and you can do CTD casts and you can use Niskin bottle casts and you collect water and you collect data. And it's very good fun. It gets a lot harder in winter because the ocean's got this nasty habit of freezing over. It's a decreasingly nasty habit because it's happening more and more rarely, but it does still happen. And when that happens, you have to go out and you have to cut a hole with a chainsaw and deploy your oceanographic instruments through these holes. This is from the underside, from one of the divers we had, taking photographs of this is a Niskin bottle going down to collect a sample for us. Inevitably, the local wildlife get curious. All of a sudden, these guys have their own breathing holes, but all of a sudden a new one is created and they want to know what's going on. So they come nosing around and wanting to find out who's up there making the noise and making this light that's penetrating their environment. So you've got to try and gently ease them out of the way so you can get your gear into the water. There's various other programs going on in and around this, including progressively autonomous technology that we're getting into. These are oceanographic gliders that we now have. We have various moorings and things. We have research cruises. But it's really this time series that I'm going to focus on today. And this is what we get back. This is from one of the cruises. The time series itself generates less than this. This, for me, is oceanographic data in its rawest form. This is my desk at Cambridge, covered with samples that we brought back from a particular research cruise. And the sampling is incredibly easy. We just fill up bottles with water and put a stopper in the top and bring them home. It's the easiest sampling you can possibly imagine. The analysis is the complicated bit. Essentially, all these water samples are then analyzed by mass spectrometry in the UK to determine the isotopic ratios of the seawater. I used to do that by hand myself, and I'm now in the very luxurious position where I pay someone else to do it for me, because it's very slow, exacting, painful work, and I'm just really, really glad that I don't have to do it anymore. But the data are gold. The data are absolutely wonderful for the studies that we want to do. So this is the time series. This starts in early 2002. The actual time series we have starts before then, but we only started sampling for 018 kind of when I joined BASS, which was 2001. So the actual 018 data that we have started early 2002 and continue actually up to the present day, and it's an ongoing program. So this is salinity. These are the years, and you can see the annual cycle in salinity. This is at 15 meters depth, which is our standard sampling depth. I'll explain this red line in just a minute. This is temperature at 15 meters depth, and again you can see the annual cycle. And you can see there's interannual variability in the summer temperatures, but at the same time you can see there is increasingly warm temperatures in the more recent years compared to the earlier years. This is ocean warming happening in front of your very eyes. This is the 018. It's a noisier measurement than the salinity, just by its very nature. But again, you can see the seasonal cycle in the 018 measurements. And this is something that I'll mention quite a bit. This is ocean mixed layer depth. So this is the depth to which the upper ocean is homogenized. And in summer, you know, the mixed layer depths are generally very shallow because you have a freshwater layer on the very surface. In winter, when you get mechanical mixing from the winds and you get convection, dense water formed at the surface sinks to a certain level. You can get mixed layer depths that are typically, in the early years, 50 meters or so. You can get extreme years. This was a big El Nino, down to 150 meters. And in more recent years, these mixed layer depths have been getting deeper in winter. And that is something else I'll come back to. Now, the thing I want to draw your eye to, you'll remember from what I said at the start, that glacial melt is isotopically light. And we know that this part of Antarctica, the glaciers are melting, much more so than the few glaciers that are advancing. So with those facts, what you'd expect is to see the oxygen isotope composition of the water to be going down, because you're putting more isotopically light water into the ocean. And this is what we're seeing. This is delta 018 over the course of the last decade, and it's going up. So that's interesting, and is actually not what we expected to see. So we can do it more quantitatively than that, rather than just say, oh, it's going up. We can actually cast it in terms of, well, how much is it going up by in terms of percentage input? And for what we do for that is we solve a very simple set of equations where we say that every water sample that we collect is a combination of three things. Circumpolar deep water, which is the ambient ocean salty water in this part of Antarctica, sea ice melt, and meteoric water. And meteoric water here is dominated by glacial melt because we're close to land. There's some precipitation, but it's really dominated by the glacial melt. And we know that the product of these fractions with their respective salinities has to equal our measured salinity. And the product of these fractions times their respective oxygen isotope compositions has to equal the measured oxygen isotope composition. So essentially what we have is three equations with three unknowns, and it's trivial to solve. So what we can do is actually calculate on the basis of the salinity data and the 018 data that we have. We can calculate how much meteoric water there is in the ocean and how much sea ice melt there is in the ocean, not just how much fresh water there is in the ocean. And this is the results of that. So this line here, this is the percentage of sea ice melt in the ocean on the Western Peninsula over the course of the last decade. You can see the values range between about -2% to +2%. And in case you're wondering how you can have a minus number for a freshwater presence, the point there is that sea ice is a cycle. It forms as well as melting. It's not like glacial melt here, which just melts into the ocean or calves as icebergs from glaciers and then they melt into the ocean. It's a one-way process. Sea ice melt, it also forms, and then the next melt season it melts. And the way we do the calculation, if you get a minus number, that means there's been a net sea ice formation from that piece of water that you measured. If you get a positive number, there's been a net amount of sea ice melted into that bit of ocean. So the values vary between -2 and +2, and you can see the seasonal cycle in the sea ice melt. In meteoric water, which is mainly glacial melt, as I mentioned, the values are much higher, typically around 4%, but varying between 2 and about 6%. And we can see, as expected, on the basis of the increase in the O18, what we're seeing is a decrease in the amount of glacial melt in the upper ocean where we're sampling it. Another thing that's actually quite interesting here is if you actually look at the seasonality of these things, the seasonality in the sea ice melt is typically 2%, maybe 3%. We're getting those same sort of numbers in the seasonality for the meteoric water. And that was surprising to me because the growth and decay of sea ice around Antarctica is often cited as being the biggest seasonal cycle on the planet. And people often say that the continent doubles in size every winter. And if you just look at the satellite images, that is how it appears. It's a massive seasonal change each year. But right next to the continent, if you're looking at the different freshwater compositions, the seasonality from the melting glaciers gives you as much as the seasonality from the sea ice. And the final point I was going to mention here is actually quite important. The meteoric water percentages are falling, but they're not just falling in winter, they're falling in summer as well. So it's not the case that in winter this water is somehow mixing away or dissipating or going somewhere, and then each summer it's just being replenished with a new influx of glacial melt. What's happening is that the high values we were seeing in summer in the early years are disappearing in the more recent years. So why is the meteoric water concentration falling? Why is glacial melt water at the Western Peninsula going down, not up, even though the glaciers are melting more? And what it comes back to, you remember I showed you a time series of mixed layer depth in the ocean earlier on. These red numbers here are those same mixed layer depths, just plotted differently. The values that we have, the years that we have O18 data for is kind of 2002 onwards. And you can see that in the more recent years, the mixed layer depth in winter is getting really quite deep compared to the early years that we had O18 data for. And what's happening there, the reason that matters is that each spring and summer, you discharge glacial melt into the ocean and you carve icebergs and they melt into the ocean. But then each winter, you're mixing that fresh water down over a much deeper ocean layer. And that's essentially diluting with salty water, if you like, the glacial melt at the very upper ocean when we're measuring it. And that's completely the opposite. It's counterintuitive of what you would expect to see. As I mentioned, what you expect to see is the glacial melt going up. Ocean dynamics is overwhelming that signal, and what you're seeing in the upper ocean is glacial melt going down. Why are we seeing these deeper mixed layers? It comes back to the sea ice. I mentioned at the start that you can't understand glacial inputs without understanding the sea ice concurrently. And I mentioned before that sea ice here is decreasing very rapidly. What's happening is each winter, the ocean is being more exposed to the atmosphere than it was in early years because the sea ice is decreasing, including in winter. And that matters for a number of reasons. Essentially, there's more mechanical mixing of the upper ocean, so the ocean is more exposed to the winds in winter, and that drives mixing in the upper ocean. And also the ocean can lose buoyancy much more easily to the atmosphere. And that means that the mixed layers get deeper because the surface ocean is made dense by losing buoyancy, and then that water sinks to deeper depths. So the reason we're seeing these deeper mixed layers relates to the sea ice change, but then the sea ice and those deeper mixed layers is what's controlling the distribution of the glacial meltwater within the ocean. So why does that matter? Why does it matter that glacial meltwater percentages are going down in the upper ocean at the peninsula? Well, I mentioned some things at the start. This is some further evidence to try and persuade you that these things do matter. I mentioned earlier on that glacial melt can fertilize blooms in the Southern Ocean because it can carry, we believe, micronutrients such as iron with it. There's a paper published very recently that looked at Greenland glaciers and the runoff from Greenland glaciers and the role of those in fertilizing plankton blooms adjacent to Greenland. And this is a photograph of Greenland, and you can see this is a meltwater stream. And you can almost see the iron in this. It's very rich. We believe the same thing could well be happening at the Antarctic Peninsula. It's not cast iron yet. This is ongoing work. This is work that's being done by Rob Sherrill and his postdoc Marie Segeret at Rutgers University. I hope you can see this. This is the Antarctic Peninsula here, and this is some data that they collected on a US cruise just a couple of years ago. This is iron concentrations in the upper ocean. And this is some meteoric water numbers that I produced from the same cruise. And you can see the values are very high inshore on the Antarctic Peninsula, as you would expect. That's where the glaciers are really discharging into the ocean. And they're much lower as you move across the shelf and out towards the open ocean. You see the same pattern in the iron in the ocean. And that really is a strong hint that these glaciers and the land systems are a source of this essential micronutrient that fertilizes the plankton bloom. So, of course, if all things were equal, and you're putting more glacial melt into the ocean, but then mixing it further down into the ocean than you used to be, what you're actually doing, or what you could well be doing, is decreasing the concentrations of the iron in the upper ocean over time. And of course, it's the upper ocean that really matters, because that's the part that's lit by sunlight. That's the euphotic zone. That's where this micronutrient can do some good in terms of fertilizing plankton blooms. So what you have here is a very strong counterintuitive result that because of the dynamics of the ocean, what you naively think would be happening by putting more glacial melt into the ocean, there's ocean dynamics happening, and what's really happening, or at least a strong indication, is actually the converse of that is happening. If you know Rob Sherrill, get him to come down here and give you a talk about this stuff, because it's really fascinating. Another reason why does this matter? I mentioned early on that sea ice around Antarctica is increasing as a whole slightly. But that slight increase is essentially driven very strongly by the big increases here, counteracted largely but not completely by the very strong decreases here. But of course, this is a fact that's loved by climate skeptics everywhere. If you say to them global warming, they'll say, well, sea ice is increasing in the Antarctic. How can global warming be real? You know, it's global. It's not happening. And of course, we all know that that misses the point. We know that, you know, the complexity of the system and these regional changes, these are the really interesting story. So what we want to do is understand why you have this regional pattern of sea ice. And there's a paper published by my colleague Paul Holland from Bass, just tail end of last year. And he's done some very nice analysis looking at how the sea ice extent is changing in response to the changing winds. And there are certainly big areas where the sea ice is being advected differently to how it used to be. And if you integrate up that effect, you can explain a large part of the small sea ice increase around the Antarctic. But it's certainly not the only theory that people have put forward. And there's a whole raft of different hypotheses that people are trying to test. And this was a paper that came out just a few days ago, in fact. This is how topical I am. But what these guys were arguing was that this is a regional effect. And to explain the increase as a whole, what they were invoking was that glacial melt from the Antarctic, which is going up, and certainly in some sectors it is floating out on top of the Southern Ocean, and it's stabilizing the ocean, And of course, it's easier to freeze cold, fresh water than it is to freeze warm, salty water. So that layer, that extra stability in that freshwater layer, is then more conducive to being frozen the following winter, and that's explaining the increase in sea ice extent as a whole, which sounds very interesting, and it's certainly a plausible theory. But the interesting thing is if you compare that with what we're seeing at the Antarctic Peninsula, and of course that's only one place, but it's still the best place that we have to challenge these theories with by looking at actual data, we find almost exactly the reverse. What we're seeing is a region of increasing glacial discharge, which is true. This is what these guys are invoking. But we're seeing sea ice decrease, and that's destabilizing the upper ocean, and it's actually reducing the surface glacial water concentrations. So instead of having glacial meltwater stabilizing the ocean, and that's affecting the sea ice production, what we're seeing is sea ice production is changing, and that's affecting the surface glacial meltwater concentrations. So on the basis of what we're seeing here, certainly in this part of Antarctica, this theory doesn't really stack up in the way that you would want it to. And essentially what we're saying is these guys are seeing effect and cause, not cause and effect. It's not necessarily the case that that's true for Antarctica as a whole. But again, this is the place that we've only got really good information to actually try and tackle these sorts of questions. So there's more to be done on that, certainly. So this is just to summarize the first part of the talk about the Western Peninsula. The climate of the Antarctic Peninsula is changing very rapidly, especially so on the western side, more rapidly than anywhere else in the southern hemisphere. Each of the freshwater inputs is changing differently, and each needs to be understood individually if we're going to get the predictive skill that we want. The rapid deglaciation that we're seeing at the Western Peninsula is actually being overcompensated by greater ocean mixing. And that's given us some counterintuitive results for where this glacial meltwater is ending up. It's not ending up in a little layer at the surface of the ocean, and the impact that it might have on both the biogeochemical system and primary production, and also on sea ice production and indeed climate. And if you remember the point I made at the start, this is what we're seeing at the Antarctic Peninsula now, but the rest of the Antarctic is predicted to look much more like the peninsula over the course of the next century than it does do at the moment. As greenhouse gas warming really bites, the Antarctic as a whole is predicted to warm, and sea ice is predicted to decrease very markedly. So the argument is that the pattern that we're seeing at the peninsula now with these counterintuitive results could well propagate around Antarctica over the course of the next century. So I'm going to move on to the second part of the talk, which is the shorter part, you'll be glad to hear, which is really about the impacts of changes on the eastern side of the Antarctic Peninsula. Now, I mentioned at the start why we're interested, or at least why I'm interested in the eastern side of the peninsula. And it relates to the Antarctic bottom water that forms there, as well as other places, and then it spreads northwards along the seabed over a large percentage of the global ocean. Now, the interesting thing is this water is changing. This Antarctic bottom water is a globally important water mass. It's important in a number of contexts, and it's actually changing. One of the ways it's changing is that it's warming. And you can see that here. This is a plot from Greg Johnson and Sarah Perkey. The pink colors show where the Antarctic bottom water sourced around the Antarctic is warming. And the biggest signal, is in the southwest Atlantic. And that's the water that's coming out of the Weddell Sea and going northwards. And that has consequences for global heat budget and sea level rise and all sorts of other things. If you make water warmer, it expands and that pushes the sea level up. It may be important for benthic biodiversity and all sorts of other things. It's not just warming. Antarctic bottom water in various places around the continent is also freshening. This is the Australian sector of the Antarctic. This is some work that was done by Steve Rintoul, just with repeat sections, and you can see that from the 1970s through to the present day, this is salinity on this axis. You can see this water is getting progressively fresher. And the theory that was put forward to explain this freshening was that this water mass, it forms on the fringes of the Antarctic, and by doing that, it's able to pick up some of this glacial-derived water. The glaciers are melting. This water can pick it up It's still dense enough to sink to the seabed, but it does so in a fresher form than it used to. So this is now looking at the Atlantic and the water that's coming out of the Weddell Sea. This is the Antarctic Peninsula here. The water that comes out of the Weddell Sea and flows northwards. As I mentioned, it's warming. This is temperature on this axis, so the move from blues to reds, so quite a pronounced warming signal in oceanographic terms. That's quite a big signal. The salinity is much harder to say. Salinity is a measurement that's, until relatively recent times, it was harder to make absolute measurements of than temperature. So if you go back to the 1950s, 1960s, data do exist, but the error bars are just so much bigger. So trends in salinity from deep ocean water masses up here are actually quite hard to put very convincing error bars on. But the evidence isn't strong. This is Vima Channel here. This is the Argentine Basin. This is the Brazil Basin. And Vima Channel is a great place to look at Antarctic bottom water because all the bottom water gets squeezed through it as it's flowing northwards up the Atlantic. But as I say, the salinity change from those measurements looks rather weak. And that was puzzling for us. We were expecting to see something a little bit more compelling than that. So what we did to try and get better insight into this was to look at data from across Drake Passage. There's a repeat hydrographic section, so lots of CTDs done by ship. Every year, it's from the British ship James Clark Ross that sails from the Falkland Islands here en route to Rothera and other places in the Antarctic. And essentially, there's around about 30 CTD stations done. It's been done pretty much every year since 1993. It's not the most obvious place to look for changes in Antarctic bottom water. And indeed, the purpose of the CTD section is really to look at changes in the circumpolar current transport, not really to look at bottom water changes. But it just turns out this is actually a really fortuitous place to look for bottom water changes for the water that's coming out from the eastern side of the Antarctic Peninsula. So these blue lines here show a very rough schematic of the circulation path that this water takes. So it can circulate around in the Weddell Gyre, and some of it can go northwards around the edge of the Scotia Sea here. But the bulk of it crosses this ridge, the South Scotia Ridge, and flows northwards into the Atlantic. But there is an offshoot that comes this way, and this southern end of this section is bathed in Antarctic bottom water. And the nice thing is that you're far enough away from the source region that all the problems you have with aliasing of seasonal signals are pretty much gone. But you're still close enough that the actual relatively subtle changes that you're looking for will still be apparent. So just by luck, this turned out to be a very, very useful data set to look at. I'll just say that the guy who actually did the numbers for this is a guy called Logue Julian, who was the postdoc we had working on Antarctic bottom water. And he's left now, and he's now working for a place called FSU in, I'm told, Tallahassee. I have no idea where that is. But if you were interested, maybe you could invite him down to give you a talk or something. So this is the data from these CTD sections. Essentially, everything colder than 0 degrees is Antarctic bottom water. So this is all Antarctic bottom water down here at the southern side of Drake Passage. And this is salinity on this axis. And these profiles are colored by year. So the dark colors are the early years, the early 1990s, going up to nearly the present day, these light colors here. And the point I really want to bring home to you here is that as you go through time, you see these dark colors on the east, on the right-hand side of this plot, and the traces move to the left over time. And that's salinity getting lower over time. The fact that these curves don't overlie, oceanographically that's important because it tells us it's not to do with mixing after the water mass is formed, and it's not to do with changes in overflow as this water crosses the South Scotia Ridge. It's to do with the actual formation properties of the bottom water itself. So you can take an average per section and you can grid the data and you can produce a time series of mean salinity in Antarctic bottom water at the south side of Drake Passage. And this is what you see from 1994 up to present. This is salinity here. And there's interannual changes, but it is going down. And it's not going down by very much. The salinity change is 0.007, which is small, but it is measurable and it is significant. And just out of interest, this is the thickness of the bottom water layer as a function of time. And again, there's interannual changes, but there's no evidence for a trend. So there's no support here for the theory that we're producing less Antarctic bottom water, but there is support for the theory that we're producing fresher Antarctic bottom water. So where's the extra fresh water coming from to explain this freshening signal? And as I mentioned before, there's different sources of fresh water that we need to consider. Is it increased precipitation on the eastern side of the peninsula? Is it decreased sea ice production, so we're producing less salty water, so that could be a freshening signal? Or is it increased glacial melt? Now, we don't have O18 on these CTD sections. It was measured 1 year, but it hasn't been measured systematically. And to be honest, because it's a relatively noisy measurement, it probably wouldn't help anyway for these relatively subtle signals. So what we do instead, in order to get insight into which of these is the cause, and bearing in mind that these are not necessarily mutually exclusive, it could be a combination of these, what we do is we investigate which of the mechanisms has the potential to cause the biggest freshening, given known constraints on how these have changed. So what we do is we derive quantifications of changes in freshwater input on the Eastern Peninsula from each of those different sources, or at least that's what we try to do. The answers are increased precipitation. What I've written here is that it's not well constrained, and that's a euphemism for we really have no idea. No one has been measuring it there, and the ice core people that do shallow ice cores couldn't really give us a definitive answer. There's been occasional measurements, but certainly not enough to give you a definitive trend. And you can look in atmospheric reanalyses, and you can look in RACMO, which is a very nice regional atmospheric analysis that some Dutch people have done. It appears small, but it's one of those things, if someone came along in future years and said, actually, I found out this is actually a bit larger than you were supposing it to be, I wouldn't be that surprised. But at the moment, we're discounting it as being the dominant cause for reasons I'll come on to. Decreased sea ice production, very possibly. There are changes in the sea ice there. You can see that in the satellite data. I'll show you that in just a second. Increased glacial melt, highly likely. This is our favorite candidate, just in terms of the volume of fresh water that it has available to discharge to the ocean. This is the same plot I showed you earlier, collapse of Larsen B. The shelf area of the ocean that we're interested in, where this bottom water forms, is just out here, immediately to the east of the Larsen Ice Shelf. It collapsed 2002, and you remember I said that it wasn't just that one-off event. Following that collapse, the glaciers that were buttressed by this ice shelf surged and discharged significantly more fresh water into the ocean, and they still are discharging more fresh water than they were prior to the Larsen collapse. Obviously, there's big uncertainties about exactly where this fresh water ends up. It's not the case that it just melts into the ocean. As Ian pointed out yesterday, this ice shelf essentially disintegrated into a lot of icebergs, and those icebergs can advect very long distances, melting as they go. So it's far from certain that, it's certainly not the case that all of this fresh water was discharged into the ocean, onto the shelf immediately adjacent to it. But the actual volume of fresh water that was discharged, that's particularly ongoing from these glaciers, is so huge. You'd only need a relatively small fraction of that to actually melt into the ocean locally to explain the signals that we see. And this is to convince you that that's been done in a quantitative way. These are the figures that Loic produced. This is an estimate of the total ice loss for the period 1993 to 2011, which is the period that we have the ocean data for. This is where the locations were from: Larsen A, Larsen B, glaciers, and these are the estimated ice loss numbers that came up with. As I said, there's uncertainty about exactly where that ice would melt into the ocean, but for the relatively small change that we're seeing of 0.007 in salinity, these numbers are huge. They're several orders of magnitude bigger than they would need to be in order to explain the signal that we're seeing. So that's very interesting. If you remember some of the things that Ian talked about yesterday, he talked about quite a lot about melting of glaciers and disintegration of glacial systems in the Antarctic. He mentioned Pine Island a number of times. And that is a region, Pine Island Glacier, that's retreating, the glacier is retreating very rapidly. The cause of that retreat at Pine Island is believed to be the warm, deep water intruding underneath the floating ice shelf and melting that glacier from beneath. That's a very effective way of affecting the glacial system because the ocean is warm. That's not what we believe has been happening on the eastern side of the peninsula. There's some work that was done by Gareth Marshall at Bass and other colleagues that investigated in quite a lot of detail why Larsen B has collapsed, and there's other work being done on this as well. And the preferred theory is that the reason for that is more to do with an atmospheric induced change rather than an ocean-induced change. And as part of the climate change that we're seeing around Antarctica is that the winds are getting stronger, the circumpolar winds are strengthening, and they're also contracting in towards the pole. Essentially, the polar vortex is intensifying. And in the Antarctic Peninsula, you have a range of mountains along its spine. The stronger winds have to go over those mountains, but then you get an effect on the lee side of the mountains that actually gives you an enhanced warming effect in the atmosphere. And it's believed that that is the main driver for the collapse of Larsen B and the big changes in the glacial systems on the eastern side of the peninsula that we're seeing. Now, when Gareth published his paper arguing for the importance of that effect on climate change on the eastern side of the peninsula, he did something that was quite rare as far as scientists do. And he actually put his head above the parapet and said he thought this was an anthropogenic effect. And most scientists, if you say, is this anthropogenic? Did humans do this? They will say, possibly. We might see more incidences of effects like this in future as anthropogenic change progresses. But it's very rare for scientists to actually nail their colors to the mast and say, I think humans did this. But that's what Gareth did. And he's a very very careful scientist. So, you've got to take his opinion seriously. But the thing is that these intensifying winds over the Antarctic have been strongly linked to anthropogenic changes, in particular ozone depletion, but also greenhouse gases have been invoked in the intensifying of these winds. And because it's a very clean signal, just the winds and the atmosphere influencing the ice sheets, that gave Gareth the confidence to actually make that statement. And of course, if he's true, and I have no reason to doubt his word, if he's true, what we're seeing is an anthropogenic-induced freshening of the seawater that's flooding pretty much all of the global ocean abyss, or at least, the very large majority of it. So that's fascinating. That's absolutely fascinating. Now, I did mention that the glacial melt was not necessarily the only cause of the freshening of the bottom water that we see. I did mention that sea ice melt could also be implicated. We're less certain about that because we don't really have the data that we want. We have satellite data that gives us sea ice concentration. And if you look at sea ice concentration in this region of interest here, which is where these bottom waters are forming, the sea ice concentration is indeed going down over time. But relating sea ice concentration to sea ice production is not necessarily trivial. You really need more information than that if you're going to do the calculation properly. So all we can say is that we can't rule out sea ice concentration as being a contributor towards the freshening that we see. For me, one of the interesting things is that even if this were a significant contributor, again, the decrease in sea ice concentration here could well be linked to these strengthening winds coming across the peninsula. And again, we believe that that could well have an anthropogenic cause. So even if this were a significant contributor, you're coming back to the root cause of did humans do this? Well, very possibly we did. So this is, to sum up, the second part of the talk about what's going on at the eastern side of the Antarctic Peninsula. What we found is the first robust evidence of freshening of the bottom water exported to the abyssal Atlantic in recent years. We're pretty convinced in our own minds that it depends strongly on changing glacial melt entering the ocean, possibly also reduced sea ice production And everything is pointing in the direction of this being related, at least in part, to anthropogenic activity. So we can take credit for doing this. As I mentioned, Antarctic bottom water has been freshening in other parts of the Antarctic. That circumpolar nature of the freshening now appears complete. Everywhere you look now, this bottom water really does seem to be getting fresher. Though the causes vary regionally. As I mentioned, in places like Pine Island, the melting of the glacier there and that freshening, which we believe ends up in the bottom water, is much more to do with an oceanographic cause rather than an atmospheric cause. Given the causes that we've seen and we've invoked, further freshening seems very likely. The winds over the Southern Ocean, we don't know how long they will continue intensifying for. If the ozone hole recovers, as it's predicted to, it could well be that these winds plateau and then decrease. Other people have invoked greenhouse gases as a partial cause for these strengthening winds. They're likely to go up for many decades to come. Further freshening seems likely, certainly for the near-term future, and possibly for the long term. And of course, that means we have to think about what's going to happen. We've seen Larsen B collapse, and we've seen the impact that that's had on other glacial systems on the eastern side of the peninsula. South from Larsen B is Larsen C, and the amount of fresh water in Larsen C and the amount of glacial ice that's buttressed by Larsen C is vast compared even to Larsen B. And if Larsen C collapses, that could have very significant consequences. And there are indications that Larsen C is becoming less stable than it used to be. There's melt ponds being seen on the surface of Larsen C, which is one of the precursors that you saw before Larsen B collapsed. If Larsen C collapses, the amount of fresh water that's discharged is likely to dwarf even what we saw from Larsen B, possibly to the point where the shelf waters become so fresh that you actually shut off the production of Antarctic bottom water in this part of the Antarctic. It's not the only source of Antarctic bottom water. It's not like this water mass will disappear from the global ocean. But it's a major part of the Antarctic bottom water that forms the lower limb of the Atlantic overturning circulation. So that's speculation. We don't know if that will happen, but it's something we have to consider. And that is all I have to say. Thank you very much for listening. I couldn't let you go without showing you a penguin, so thank you very much for that. And yeah, I hope you found it interesting. Thank you. Any questions?
I'm interested and intrigued by your increase in your winter mixed step layers.
Yeah.
Those were measured at Rothera?
Those are measured at Rothera.
And so would that, when you talk about decrease in sea ice, do you mean that the Marguerite Bay Polinias, the extent of it is increasing during winter, so you're experiencing more open water at Rothera?
Exactly right. What we're seeing is, because it's really the fast ice that we used to see very extensively around Rothera, around Marguerite Bay, around that part of the peninsula. It's really that fast ice in winter that's decreasing. And I showed a picture of people doing a CTD cast from a sledge. Some winters now, they don't ever get to do that, just so there's no fast ice that forms there. You know, ice forms, but it moves around. And it's nowhere near as extensive or as rigid as it used to be. And of course, the people are hugely disappointed because they love going out with the chainsaws and cutting big holes in the ice and playing with the seals in a humane way. But increasingly, they don't get to do that. And it really is the case that in winter, the polinias are increasing and the fast ice is decreasing, and that's explaining what we see. David.
So I have a comment and two questions. The comment is relative to chainsaws and cutting through ice, in the United States, in the central United States, they call that ice fishing. But what they do is they actually up the ante and they drag out a small house that they lie on top of it with a heater. So perhaps you could increase the quality of life out there if you wanted to.
We don't want the people getting soft. I mean, Britain has a long heritage of suffering in the Antarctic. And occasionally taken to extremes, I agree. But, you know, we don't want our people getting soft.
I should have realized. The first question is regarding the West Peninsula. Your isotopic work is sort of like a mass balance with relative proportions. And why don't you increase, would it be a wise choice to include flux inputs also from the sources so that you can have a flux isotopic mass balance?
Yeah.
Is the first question. On the east side, I have a question, which is why don't you turn this into density space rather than salinity or temperature space? Because the two you're seeing is a freshening and an increase in temperature, which is going to obviously change the density quite significantly. And so, predictably, when is North Atlantic deep water going to undercut Antarctic bottom water?
Okay. The first question is the easiest one, so that's the one I'm going to answer first. We have done that. What we've done is taken the best estimated fluxes from RACMO, which is a regional circulation model. It includes the best estimates we have of precipitation. And then use the surface mass balance from that with sort of catchment areas to estimate the discharge rates into the different places along the West Antarctic Peninsula. And then by using that information in combination with the oceanographic O18 measurements, you can actually work out things like residence times of these waters in the ocean. And that, one of the plots I showed was from that paper. It's just coming out in Journal of Climate. And originally I was going to show you that, but then, you know, there's other things that I was actually more excited about. So we have done that, and it's very important, and we're going to keep doing that. And the really nice thing that we're doing that supports that work is actually now we're getting, from the Lawrence M. Gould, the LTER program, they do a grid of stations along the peninsula every year. They're now sampling that for O18 and sending the samples to me. So each year we're getting not just a point from which we have the O18 data, we're actually getting a volume. From across that whole grid, we can calculate a volume of meteoric water that's there at that time. And then we compare that with the known inputs, and we've got flux estimates. Second question about the density. I mean, we do look in density space. Density is one of those things that, I mean, maybe if I showed you the plot, you'd find it easier to envisage. I showed you the TS plot of the changing curves. In the background of that, there were the density profiles. So you can actually look and see how a salinity change is impacting on the density of the bottom water and how a given temperature change is impacting on the density of the bottom water. And the answer is it is. You know, and as I said at the start, salinity is the controlling variable of the equation of state for seawater. So if you make the seawater fresher, at low temperatures, it's a very effective way of making it less dense. And we are doing that. When will North Atlantic deep water start undercutting Antarctic bottom water? I'm really not sure, but I think it's probably going to be around about the same time that the Arctic is ice-free in winter. So if you want to have a bet for a bottle of wine about that, we could do that. Yes?
This is probably an open-ended question, but do you know some of the major implications for shutting off Arctic bottom water in this area?
The implications? That's a very good question. The honest answer is no, but we can speculate. Essentially, if you shut off one source, it's unlikely that the other sources will compensate for it somehow. So if you shut off this one source, the actual flux of bottom water that you're pushing out into the global ocean is likely to go down. Not to zero, but it's likely to go down. What that means is that given ocean mixing, given the way the ocean works, it's likely that the warming that we're seeing in the bottom water will get stronger. It's likely that oxygen concentrations will change in the deep ocean. And it's also very possible that the amount of carbon that the ocean is sequestering from the atmosphere will change. And at the moment, there's a debate going on as how important is Antarctic bottom water as a mechanism of taking down anthropogenic carbon from the atmosphere and storing it in the ocean. At various times it has been important. Whether it's important now, quantitatively, there's a lot of ongoing work on that. But if that were important, that would mean there's more carbon left in the atmosphere than there used to be, and that would mean that global warming would accelerate even faster. And there's possibilities that it'll impact on benthic communities that very often the animals on the seabed, they're evolved to cope with low temperatures. They happily deal with temperatures around about 0 or even colder. But they're very poorly evolved to cope with changes in temperature. So if you start making them warmer rapidly, you can end up with impacts on the ecosystem anyway, possibilities of population losses. That's wild speculation. Don't quote me on any of that. It's already on the web, thank you. That makes me feel a lot better. Thank you very much. Yes?
Of course, being able to identify anthropogenic causes is interesting and important, and we don't do it very often because it's hard to fingerprint it. How were you or Marshall? I wasn't clear on how you or Marshall able to fingerprint this and come to the conclusion that it's anthropogenic.
Well, I think the strengthening of the winds being strongly influenced by anthropogenic causes. There's been an awful lot of work on that. The atmospheric community has been working for many, many years to try and attribute why are the winds over the Southern Ocean getting stronger. And they've run models with and without ozone depletion, and they've run models with and without greenhouse gas emissions, and they've tried to constrain the range of natural variability, and they've done ensemble runs to say, are we confident at the 95% level? Are we confident at the 99% level? And everything is pointing in the direction of there is an anthropogenic cause, or at least an anthropogenic contribution to the strengthening of the winds. And I wasn't involved in the work. It's Gareth Marshall's work and John King's work. But then they've been looking at the winds that cross the peninsula, and they've looked in a lot of detail at the mechanism. It's called the Föhn effect, the mechanism for how that signal, the warming signal, is generated because of the strengthening winds over the peninsula. It's a well-known effect in meteorology, and it's really that connection that allowed them to put together the confidence that they have that there's an anthropogenic signal within there.
The models, as the ozone depletion diminishes, do the models show that there may be a slowing of that warming, or will the CO2 increase more than compensate? What's the proportion, I guess, of the two effects?
I think that's a very good question. I think, and of course, when someone says that's a very good question, that means they don't have a very good answer. I mean, that's what I'm saying. I think increasingly, the ozone depletion is seen as the main of the possible anthropogenic cause. And the greenhouse gases, which were favored by a number of atmospheric groups for a long time, I think increasingly, if my understanding is correct, that's seen as being probably the lesser of the two. And if that's true, what that could well point towards is as the ozone hole recovers, the strengthening winds could slow down, and the winds themselves could actually slow down. But I don't think anyone knows with any great certainty, because just the mechanisms that are there and the fact that you can have a change in the radiative balance in the atmosphere because of greenhouse gases, even if it's not been the dominant cause so far, it doesn't mean it will always not be the dominant cause. So I think there's a great deal of uncertainty about that. Sure.
I realize you didn't address this in your talk, and I know absolutely zero about the topic. But could you comment about the sub-ice lakes, and to what degree are they expanding? Are they being connected? And will they eventually discharge into the ocean?
Could I comment on that? Not with any authority either, I'm afraid. I mean, my understanding of that is that these lakes have been known about for some time, but it was relatively recently that people actually discovered how interconnected they are, and that you can have catastrophic events happen subglacially, that, you know, flood events connecting one subglacial cavity to another one. Can that water end up in the ocean? Certainly in some cases it can, and inevitably I think it will. But that doesn't mean that, you know, things like Lake Ellsworth or Willans and places like that will necessarily be discharged to the ocean anytime soon, because they've been there for, you know, very long periods of time, some of them. So I think, if my understanding is correct, and I think there's people here know more than I do about this, the actual dynamic nature of that system is only beginning to be appreciated, but it's certainly not the case that all of the lakes are, you know, flushed and renewed regularly. But that's a subject I don't really claim any expertise on.
There are more questions.
This is regarding the data collection. You mentioned about the CTD cast, and you showed some glider picture there.
Yeah.
So can you kind of comment upon that experience as to using the gliders, and whether you used anything additional sensors to it? That is one part. And also I wanted to know how this data collection in terms of the Antarctic program is connected to the global ocean observing initiatives and stuff.
Yeah, okay. The gliders, yeah, good question. It's relatively recently we got into gliders. And the picture I showed at the start and said that I took it when I was in the Antarctic Peninsula. The reason I went there was to take 2 oceanographic gliders and deploy them from Rothera. And the reason that I was keen on buying some gliders and doing this work was because we have our time series. And you know, as you can tell, I love the time series, but it's only one point in the ocean. And actually saying how well that point in the ocean relates to all the other points in the ocean is not necessarily straightforward all of the time. Certainly there are very large signals within that time series. We see El Nino signals, we see southern annular mode signals, we see global warming signals. There's also local signals. And knowing how to decouple those two, ideally you want spatial information to go with the temporal information. So I thought, great, gliders. And it was the guys from Parma, and Oscar Schofield in particular, that got me into these gliders. And he was saying, you've got to get some of these gliders. So I went and bought a couple of gliders. And then I took them to Rothera this season. And it's probably the most stressful experience I've ever had in science. Because, you know, these gliders are about £120,000 each, which is, you know, not a trivial sum of money. And you put them into the ocean and you just watch them sail away. And you think, okay, let's go and get a cup of tea. Yeah, tea with rum in it. And it was working fine, and the data was coming in, and I was getting really quite blasé about this, thinking this is the way to do science, you know. And then one of the gliders just out of the blue stopped reporting data. And, you know, and it was a truly horrific feeling, thinking you might have just thrown away £120,000 for 3 days of data or whatever it was. And of course, you know, we were going through on our heads, why is this glider not talking to us anymore? Is it stuck on the seabed? Has it just imploded and is in pieces on the seabed? Or is it stuck underneath an iceberg? And, you know, we had no way of telling because we couldn't talk to the glider. And I was busy composing my resignation letter to British Antarctic Survey. And then, you know, about a day later, this glider popped up and started talking to us again. And it just, out of the blue, just ping, here I am, what shall I do now? And so we scrambled. And there's a guy called Ben Alsop from Massachusetts who works for the company that made these gliders. He was fantastic. He pulled his car over to the side of the road when this message appeared on his mobile phone and was trying to control the glider by his phone, which was just incredible. And it turns out it was stuck underneath an iceberg. So it come up underneath an iceberg, and it was stuck at 40 meters depth for about 24 hours. And it could have been there for weeks, months, years. You know, icebergs can exist for years, depending on where they're formed, where they go. But just either, we don't know why, but you know, it could have been just the waves moving the iceberg around, or it could have just been that it wasn't, you know, very firmly lodged, and just the glider moving when it's trying to change its attitude. Just released it and it came back up to the surface. And after that, it worked perfectly. Will we do things differently next year? Yes. The nice thing we have is being at Rothera, there's an airstrip. So we have planes coming in and out all the time. And what we're going to do is, we started doing it this year, we're going to do it in a much more systematic way, is get visual photography in real time from the aircraft flights. Because you can see the big icebergs by satellite. Those aren't the danger. The danger is the little ones that you can't see by satellite, but you can see them by aeroplane. So we're going to use that information in a much more systematic way. You asked the question about how all this relates to the global ocean observing system. This is something that is dear to my heart. The Southern Ocean has always been the biggest data desert in the world, partly because it's so far away from the countries that have always previously been the oceanographic powerhouses, the United States, Europe, Russia, places like that. That's changing. Partly also because it's a very harsh environment to work. You know, people like me can lose gliders there very quickly if they're not careful about what they're doing. So the amount of data that we have, even now, even with things like Argo, is really poor compared to the rest of the global ocean. So what we're doing is there's an initiative called the Southern Ocean Observing System. And what we're really trying to do is turn that around. What we're really trying to do is get enough oceanographic equipment deployed in a concerted way with all the different nations working together to ensure that the data coverage is at least acceptable. Because the big problem at the moment is not that it's poor, it's unacceptably bad. You know, there's changes that we're just not understanding because we don't have the data. You know, we can model things and we can come up with any number of hypotheses for why something's changing, but unless you can challenge those models with observations to say which one's right and which one's wrong, you know, we're really limited in what we can do. And the nice thing about Antarctica, of course, is that it's not owned by anybody. You know, any country really that wants to do science there can go and do science. And there's organizations like SCAR, Scientific Committee on Antarctic Research, that exists to try and coordinate that science. It is the continent for science. So something like the Southern Ocean Observing System, there are mechanisms that we can use to try and make that work. It's in its infancy, it's only a year or two old, but there are already signs of it gaining momentum because the scientific reasons for wanting that information are so powerful. So, yeah, great question.
Yeah, last question.
Just to follow up on your answer here about the gliders, are you considering changing some of the technology in the glider to, first of all, have videos to see if the seal is bumping around, knocking it out of the way? Two, are you talking about maybe having some power ability so that if it does get stuck, it can maneuver and not focus on the gliding technique, but some other techniques?
We, in combination with the manufacturer, we're investigating various options like that. They're already working on a sort of hybrid glider, so it can glide when it wants to, and that's very useful because it saves power, it saves battery life, which is why they have the incredible long duration that they do. But they're working on one that glides, but also has a propeller, so when it needs to fly horizontally or even backwards, it can do. And for things like when it gets stuck under ice, that would be very valuable for us. There's other hardware fixes you can put in place. The standard issue glider has a downward-looking altimeter, so it doesn't hit the seabed. An upward-looking altimeter all of a sudden starts to look really sensible. So, you know, we're going to try and push those things forward in combination with Web Research or other manufacturers.
And is the acronym for your Southern Observatory in the Southern Oceans SOS? Or
No, but maybe it should be. This is SOOS.
Okay. It's just about 3 o'clock. As yesterday, we have some refreshments, some goodies next door. The next talk is going to actually probably show a couple of more pictures of actual biology between sea ice and fish. And again, let's thank Michael.
Thank you.